Okay, so let's have a look at this part of the syllabus, nth root of a complex number. But I'm going to pick a very particular number, and I'm going to solve this equation here. Now, first of all, your first thought might be, apart from it's a z and not an x, your first thought may be to use the factor theorem, where you quite clearly see z equals 1 is a root, and therefore z minus 1 is a factor, and we could try and fill in the rest of the quartic here, but it would be difficult. But I'm going to come back to that. Instead, we will rearrange this equation so that it reads z equals 1 to the fifth. Now, this procedure here works for all sort of complex numbers, but I'm going to do it for this very special complex number 1. First of all, you must draw a little Argand diagram because it's essential you get the argument and modulus right. Now, obviously, 1 is a very simple case, which is just equal to cis of 0. Its modulus is 1 and its argument is 0. So I can use de Moivre's theorem and I get cis of 0 times a fifth, which is cos of 0 plus I sine of 0, which is 1. But I can say, well, I could have called the angle 2 pi. Wouldn't make any difference. That's still equal to 1. And so I can use de Moivre's theorem. I can't put equals there. I'm going to get a different root this time, cis of 2 pi over 5. And I can go round twice and 3 times and 4 times. And I could go round again 10 pi over 5, but that will go back to my original 1. Cis of 10 pi over 5 is 1. So you will always get 5 roots for a quintic equation, always. Now, let's think about these. First of all, I can plot them on an Argand diagram. There's the first root, number 1. Now the second root here is cis of 2 pi by 5. 2 pi by 5 is 72 degrees. Remember, it's got a modulus of 1. So I'm going to label this one. What letter shall I give it? I hope you already know which letter. It's going to be omega, or W, if you prefer. Now, what is omega squared? That is this number squared. Well, this is just a cis. So when we square it, we're going to get de Moivre's theorem yet again, which is the next one. So this second one round here, cis of 4 pi by 5, is omega squared, omega cubed, omega to the 4th. Now notice that they are, in all cases, not just for the cube root of unity, but in all cases, they are evenly spread around a circle. And that means there is some symmetry here. In the case where we are solving a real number to a power, you can be sure that there will be one root that is real if it is an odd, and there will be 2 roots that are real, one here and one there if it were even. So, for example, squared would definitely have a plus or minus root. But the other roots will be evenly spread around. So that one is fixed there. Now, the other roots have 72 degrees between them. Now, just by symmetry, I hope you can see that this one and this one are reflections of each other. Now, what does that mean? It means they have the same real bit, but a negative of the imaginary bit, which means that they are conjugates of each other. And similarly, omega squared is equal to omega squared conjugate is equal to omega cubed. I could move the conjugate to there, wouldn't make any difference. Now, when you add a conjugate pair, what do you get? Omega plus omega to the 4th. Well, the real bit is going to be added twice, and the imaginary bit is going to cancel out, so we can be sure that that is real. If I add omega squared and omega cubed, it can be sure that that is real. And if I add the 1, it means if I add up all the roots, it is inevitably real. I'll just rewrite them in order. Oops. So we know that that is real. It's also true that if I add up the 3 real parts of the right-hand side, so I've got a positive there, I've got a positive for this one, and I've got a positive there, that is going to add up to these 2 positives exactly. In other words, this is equal to 0. Got a nice little proof of that. Let's say we don't know what the roots add up to. So, oops, I'll just call it k. I'm going to multiply through by omega. So I get omega squared, omega cubed, omega to the 4th, omega to the 5th is k omega. Now, what is omega to the 5th? Well, you must keep in mind what omega means. Where did it come from? It's all the way back here. This one here is omega. Where did it come from? It came from the fact that it is the 5th root of 1. So if we raise it to the power 5, of course, we get 1. So I'll put that in. So in fact, this line here, when I multiply through by omega, doesn't change, which means that these 2 things must be equal. So k is equal to k times omega. What possible value of k makes that work? Well, there is only one possible value, which is 0. Let's just look at a couple of other features. Let's go back to this diagram here. Let's look at these 2. You know that they are conjugates, these 2, but they don't look like conjugates. But if you examine this one, how could we write this in a different way? Cis of 8 pi over 5 is this angle here, 8 pi over 5. I could just simply say that angle. So what is this angle here? Well, it is cis of negative 2 pi over 5. By the way, when you have a negative inside a cis, it is obviously equal to cos of minus 2 pi over 5 plus I sine of minus 2 pi over 5. It can be written as cos of 2 pi over 5 minus I sine of 2 pi over 5. Now generally you don't want to do this. This is bad because we really love cis. Cis has so many, is so powerful because of de Moivre's theorem. This is just an awkward complex number. So more normally, if you see this in a question, you have to have the gumption to realize that because cos is an even function, I can put a minus sign in there. And this minus sign can be incorporated into the sign because sine is an odd function. So these 2 expressions here are equal to each other. The top one is the useful one. Nevertheless, for this chat, let's just have a look at this number here. What happens if I multiply this number by, what's it doing? So I'm going to multiply longhand this root by this root. What will I get? Well, here it is. There is the first root and there is the last root. I'm going to multiply them together. So I am going to use the fact that cos of minus 2 pi by 5 is just that. And this minus sign in the sign can come out. And now what do I have here? This is a plus b times a minus b, difference of 2 squares. And so I can do that. So I'm bound to get cos squared of 2 pi by 5. Now it's a squared minus b squared, but I've got an I squared there, so it's plus sine squared of 2 pi by 5, and that is 1. Of course, you should have known that already, because if I multiply w by w to the 4, of course I'm going to get w to the 5, and remember what w is. It's the fifth root of 1, so raising it to the power of 5 is bound to lead to 1. Lastly, I now know what the factorization is of this. It is z minus each of the roots. So I can just write that out. So I've written it out. Notice I didn't write 2 pi, 4 pi, 6 pi, 8 pi. I've written it as 2 pi minus 2 pi, 4 pi minus 4 pi. It's the same thing, but I put them in conjugate pairs. And what I want to do is combine these two and those two. Now if I'll just do this one. If I combine these two, obviously I'm just simply multiplying in the normal way. I'm going to get a z squared. I'm going to get that times that. No, that is exactly what I just did. It's 1. And then I'm going to get a couple of middle terms, which is z, well, I'll put a minus sign there, z times cis 2 pi by 5, and I've got that one, which is cis of minus 2 pi by 5. Now what is this equal to? Well, always remember cis is just notation, it's just an abbreviation. It's cos of 2 pi by 5, cos of 2 pi by 5 plus I sine of 2 pi by 5 plus cos of negative 2 pi by 5 plus I sine of negative 2 pi by 5. And those two cancel because sine's an even function. The minus sign comes out. This minus sign here we can just ignore. And so I end up with z squared minus 2z cos of 2 pi by 5 plus 1. So that is one of the quadratic factors. Now it's a quadratic factor that has imaginary roots, and the other one is lovely.